Hi everyone, I'm Siqiang.
Hi everyone, I'm Subarna. We are from the Data Systems Lab at Harvard University.
Today, we are going to talk about Rosetta, a robust space-time optimized range filter for key-value stores.
We did this work jointly with the other members of the lab, Rafael Nev Wilson, and our advisor Stratos.
I will be covering the first half of the talk, and then Subarna will take over the rest. The main idea we want to introduce here is how to design range filters for improving range queries in key-value systems. The range query cost is divided into disk I/O costs and CPU costs. We show that range filter is closely related to disk I/O costs, while its CPU-related computation is only a minor portion. We will demonstrate that in the balance between false positive rates and probe costs in range filter design, trading probe costs for false positive rates is beneficial for end-to-end system performance. Now, let's first give some background knowledge of key-value stores. Key-value stores are everywhere. They increasingly serve as the backbone of applications across the areas of social media, flash memory firmware, geospatial databases, time series databases, and graphs. Mainstream write-optimized key-value stores use a data structure called the loss structure merge tree or LSM tree. It allows systems to target write optimization while also providing very good point read performance when it's coupled with Bloom filters. As LSM-based key-value stores need to support fast writes, the ingested data is first inserted into a memory buffer. When the buffer grows beyond a predetermined threshold, it's flushed to disk and periodically merged with the old data. This process repeats recursively, effectively creating a multi-level tree structure where every level is sorted and larger levels contains older data. When doing point reads, it potentially needs to access every disk level for qualified keys. Each disk page of every level is covered by fence pointers in memory with block min key and max key information. So when accessing each level, we can directly go to the right block. But this still cannot avoid IOs at each level. To support more efficient point reads, LSM tree use in-memory Bloom filters to determine key membership within each level. If the filter returns null, further accessing the corresponding disk level is avoided. If at some level we find a qualified key, then checking the next levels are skipped. Similarly, when we perform range queries instead of point queries, we need range filters instead of point filters. However, range queries are much harder. For example, unlike point queries, the range query has to check through every level regardless of whether the current level contains qualified keys or not. The state-of-the-art methods for range queries in key-value stores include the following. Let's consider one disk level in the system. Fence pointers can rule out disk blocks with contents that fall outside the target key range. Modern key-value stores utilize prefix Bloom filters that hash prefixes of a predefined length of each key within Bloom filters. The state-of-the-art succinct range filter called Surf can filter arbitrary range queries by utilizing a compact tree-like data structure. There are some open problems in range filter design though. While current methods can handle very well large query ranges, short and medium range queries are significantly suboptimal. In addition, existing methods lack support for workloads with strong key query correlation. For example, we have key 26 and close query range 27 to 28. Their binary representations share a long prefix indicating a correlation. Also, there could be chances where we can make use of the workload distributions to improve performance. Finally, current range filters cannot help much or even degrade the point query performance. Considering range filter design in systems is more complicated. From a system point of view, our design intuition is we can afford more probe costs in filter design when optimizing end-to-end performance. In key-value stores, range filters are stored in memory, so filter probe is fast, while data is stored in much slower disks. Suppose we want to check the existence of a range. The range is first fed into the filter, incurring certain CPU costs, including filter probe cost and system-related operation costs such as seek and deserialization. Interestingly, the filter probe cost is only a small portion of all CPU costs. There is a probability that when the range is empty but filter returns yes, We call this probability the false positive rate, or FPR. So disk I/O cost is positively correlated to FPR. The overall cost is the sum of CPU cost and disk I/O cost. Note that when given a memory budget, any filters trade between the filter pool cost and FPR to optimize end-to-end performance. If we can optimize more on FPR, the disk I/O cost will be significantly reduced. Even with a higher pool cost, the overall system cost is still significantly improved.
So with this design intuition, we proposed Rosetta, a range filter specifically designed for KeyValue stores. Rosetta comprises of a series of hierarchically arranged Bloom filters, where the number of Bloom filters depends on the maximum length of keys in the workload. For each key to be inserted, the key is first decomposed into all possible prefixes, and then each prefix is hashed into the particular Bloom filter whose level matches the length of the prefix. For example, you'll see that prefix 100 has a length of 3, and so it's hashed to Bloom filter 3. Now, after inserting an array of integers to Rosetta, the Bloom filters at each level contain multiple prefixes of different length. Interestingly, in principle, Rosetta takes advantage of some of the logical patterns coming out of this physical layout. Let us consider the least significant bit of all prefixes. If we mark the existing ones with red and the non-existing ones with black, we start to notice a binary tree-like structure where different paths represent different prefixes. And this basically takes the shape of a segment tree that is implicitly realized within Rosetta. Okay, so with the use of the segment tree, let's look at how range queries work in Rosetta. Firstly, Rosetta decomposes any range query into its corresponding dyadic intervals and identifies the subtrees for each of the intervals. For each subtree left to right, it looks for the prefix denoting the beginning of the subtree. So in this example, the prefix for the first subtree is 0011, which is absent. So Rosetta picks up the next prefix, which is 01. It finds 01 in the tree, and at this point it begins to doubt that, is this a true positive or a false positive? In order to be fully sure, it keeps traversing downward to the leaves until it finds at least one prefix starting with 01. If it finds one, the probe terminates and the filter returns an overall positive, else the probe keeps going on. Now, there are multiple ways to manipulate the CPU FPR trade-off in Rosetta. If we look at the very basic design, one can choose to terminate the probe early by not penetrating all the way down, which reduces the probe at the cost of higher false positives. And of course, on the other hand, going down to the leaves can improve FPR at the cost of high CPU. Now, Rosetta, being a more CPU-intensive filter by design, we prioritize going through the deeper level Bloom filters more than just terminating the probe early. And this way, it takes more time for Rosetta to answer a query, but then there are way fewer false positives. On top of the basic design, we've implemented more advanced designs by firstly excluding some of the upper level Bloom filters as they mostly return true positives. And then we strategically assign memory differently across different Bloom filters, which brings the FPR further down. Now, let's see how Rosetta is integrated with industrial KeyValue stores like RocksDB. There's a Rosetta instance for each run at every level, which is further decomposed into the set of Bloom filters. For any query, firstly, each Rosetta instance is deserialized and converted to meaningful in-memory filter objects which can be queried. Next, each Rosetta instance is probed. If the Rosetta returns a positive, we perform the seek operation, which involves pulling the correct fence pointer blocks followed by reading the data blocks. And this happens for all the different levels of the tree. Now let's move on to the performance evaluation, where we are going to take a look at the end-to-end performance. We'll compare Rosetta with 3 baselines, and all of them are integrated on top of RocksDB. So we have the basic RocksDB with only fence pointers, the prefix Bloom filter, and surf. For this experiment, we consider a uniform workload and set an identical memory budget for every filter. Firstly, we observe that fence pointers have the highest latency. As they are less likely to detect empty range queries, they end up doing I/O for almost every query. Even for prefix Bloom filters, they encounter a large number of prefix collisions as the range size increases. Although surf outperforms both these baselines, the core design still relies on a tri-culling strategy with partial prefix information. Rosetta, on the other hand, significantly reduces false positives by its ability to check for the existence of variable length prefixes for all dyadic intervals. Now, this being said, note that it's not just the reduced FPR that contributes to the increase in Rosetta's performance. For example, if we take a closer look at both Rosetta and Surf and try to isolate the different CPU and I/O overhead, what we observe is that the filter probe in Rosetta is about 19% of its overall CPU cost, whereas it's only 5% in case of Surf. Although probe is significantly higher in Rosetta, it's basically this CPU intensiveness of the design that leads to bigger gains. So Seek dominates the overall CPU cost, and a large part of Seek is directly influenced by the FPR of the filter. Therefore, sacrificing the filter probe not only lowers the FPR, but also reduces the overall CPU overhead, making a big difference in the end-to-end performance. Now, this being said, for tighter memory budget, however, we observe that Surf can perform better, specifically for long-range queries. We also have a bunch of interesting results included in the paper showing that even with a complex design, Rosetta's construction cost due to compactions in the tree adds minimal overhead in the end-to-end performance. For point queries, Rosetta maintains the same performance as that of RocksDB. It also supports diverse data types such as strings and can work with a reasonably low memory budget where other filters are not applicable. Overall, our results indicate that both Surf and Rosetta can complement each other across different scenarios. For example, for short and medium range queries, Rosetta works better. For long range queries, like we've seen, Surf performs better when the memory budget is low, and then Rosetta takes over with high memory budget. To further bridge this gap and enjoy a filter that can fit any workload scenario, one of our ongoing directions focuses on bringing together the best of both worlds. The core idea is a workload-aware design that consolidates the structural advantages coming out of both Surf and Rosetta so that we can have a tailored filter design for every application. With this, we'd like to conclude the presentation, and thanks so much for listening.